Okay, so today we have an unusual stone. This came off of one of my larger pieces, and this kind of separated off of the bottom of it, and it looks like this in its entirety. The entire thing is either black or gold, and it's either platinum, which is the black stuff, or gold, which is the gold stuff. And there's rather a lot of it in this particular little piece. And in fact, from the whole piece, the whole thing is, a big chunk of gold platinum alloy, and it is bonded together around other stuff that was in the melt when it solidified, when it cooled. And these other things are notably silicon carbide or aluminum oxide, but looking mostly like silicon carbide. This might be aluminum oxide. They usually form in pretty regular hexagons, aluminum oxide does, and silicon carbide forms in tetrahedrons, and that's what you see here is the face of the tetrahedron. The way to make a tetrahedron is, if you forgive my dirty fingernails, I've been working. If you hold your fingers like this, and this together, it makes a tetrahedron, a four-sided figure with four corners and four triangular sides. So our fingers make them kind of automatically, and everything else does too when it has bilateral symmetry with a twist, I guess. It's just got a little twist to it. And this one's kind of the long way, but pinch together here, pinch together on this side, and three sides, bump, bump, bump. And they meet in the middle, on the fourth side. So there's two tetrahedrons that are joined together, and they kind of twist, just like the way your fingers do a little bit. The shape that your fingers make when you join them together like that, or the other way, like that. So, and that would be like back here. And so, anyway, what we have here is things that end up in what are called interstitial sites. Okay, so there's planes of cleavage that go through the structure of the crystal because it's cubic. Okay, because AU and PT are basically the same size, and they form in a very definite north-south cubic arrangement. Gold, platinum, gold, platinum, gold, platinum, gold, platinum, gold, platinum. See what I mean? And this looks like, you know, that it's called somebody or another's triangle, and you make a triangle, and then you can cut that triangle up into other triangles. There it is. Cook's triangles, or no, I think that's Cook's snowflakes. Yeah, might be Cook. Koch. Anyway, those triangles are, you know, I think every kid that's ever played with a triangle came up with the same thing because anybody can see it. And the more you slice it into triangles, the more triangles you have. And that's what they do to paper dollars, right? Yeah, it has a value of this big, and then you cut it into smaller and smaller and smaller slices. Because you only get so much pie. And no matter how many times you slice it, it's still the same piece of pie. So anyway, here we are. This is AuPt, gold platinum alloy, and there's more of this than there is anything else on the face of the planet. The volcanic ash from the KT extinction event looks pretty much like this when it solidifies. This is what volcanic ash turns into, because that's what this stuff is. That's what this stuff is. And this stuff, too, is covalent metals. They share covalent bonds, not metallic bonds. They share covalent bonds like diamond and silicon carbide do, because they form at great depth. When I melt it with my plasma torch, it cools rapidly, and it forms into metals. So you can count on it forming into these crazy dendrite type crystals, and here they are. There's one here. It's kind of leaf shaped. That's what they are. They form a leaf shape. And they're fractal. And they're half and half. Half platinum and half gold. and the closer, the further in you drill, the more platinum and gold you see, no matter which side you choose. It alternates gold, platinum, gold, platinum, gold, platinum, all the way down to the littlest littles. And the thing is, they're diamagnetic. Both gold and platinum are diamagnetic. They're not magnetic. They're diamagnetic, which means they will resist an applied magnetic field. So, what does that mean? when it comes to large objects, because something, the Earth itself is made out of this stuff. I'm not making this up. I didn't make this thing here. I found it in the river. I found a whole bunch of them because that's what there is there. That's all there is there, pretty much. And I don't know why nobody else noticed this before, but they didn't. And maybe they just don't know as many different kinds of things as I do, but and that's possible. It's possible. I found this not because I got lucky. It had nothing to do with luck. I found this stuff because I predicted that it would be here. I predicted that the gold and the platinum would join together in double covalent bonds. And when I tested, indeed, it's 10 on the Mohs scale of hardness. See that shiny stuff there? That is as hard as diamonds. It's a metal. It's a platinum metal that's as hard as diamonds. It carries heat away like diamonds do. That is, when I drill it with a diamond drill, the heat gets whisked away, gets carried away somewhere other than where my drill is working, and it does not transfer into the rest of the stone. It just goes away. Just goes away. This is a metal that's as hard as diamond. And we can make our machines out of this stuff. It's the bones of the earth. It requires no processing to use. You just use it the way it is. I can machine this just exactly like a piece of steel or aluminum, and it will form a perfectly smooth, flat surface. And when we make metals out of it, when I melt it into a metal, I believe I'm getting a room temperature superconductor. That's what I think it is. And this is, basically the dirt in the middle of the river out there. That's what this stuff is. The dirt. And silicon carbide. That's what this stuff is. Bits of platinum, silicon carbide. And the platinum is black because it's lacking a neutron, so it's absorbing energy instead of reflecting energy. And of course, if you shine it up, it reflects like mad. And glows blue even. So there it is.